All right, so let me see. How was it? All right, we can start. Okay, great. So thanks a lot for making the trip on the last day of the lectures. You'll be rewarded by learning about one of the kind of most cutting edge things we're going to discuss in this lecture. In the end, it's called modern deep learning. So it's that's right to not only talk about perceptrons, but also some modern things. And so we're going to talk about the thing that you heard about in the news, diffusion models, before we start. So I guess you've seen this. Okay, if you haven't signed up for the exam, sign up for the exam. There was I think a demand for office hours or Q&A for the same. So next week I'm available on the Monday in the tutorial slot. So we can meet there, or on Wednesday between 4 and 6, basically. And after that, the week after, I'm traveling, and so we can try to discuss over Discord. And then I think the week after, I'm back, and so if there's still demand, we can also meet in the week after. But I'm organizing a conference, so I'll still need to see what my availability is. But okay, next week, Monday or Wednesday, I'm happy to chat. If that's something you want to do. Okay, otherwise just try to write your questions in Discord and we'll try to follow them up. Okay, so we have the last lecture of the semester, and okay, so just as always, kind of what we discussed last week. So last week we kind of went more towards generative models that kind of model the likelihood explicitly. So we have a high dimensional likelihood P of X. We don't know a priori what this likelihood is because we only have samples, but we want to learn the likelihood. And so we are trying to approximate it. And then we made a little bit of a case. Okay, why? I mean, in the end, kind of standard supervised learning also tries to approximate the likelihood. And so why couldn't we use this? And there were various discussions on how the flexibility of the models that we usually use in supervised learning is not great. And so then we went into autoregressive models and normalizing flows. Okay, so but then this is not the end of our kind of generative model adventure, because there's a new kid on the block. So for those, okay, this is before you were born, likely. So this was one of the early boy bands in the early 1990s. Called New Kids on the Block. And so there's one more generative model that we should discuss. And this is the generative model that produces images like this. So this is, for me, totally mind-blowing that this is generated by a machine learning algorithm and not some kind of artist. And so this is using a system or like a model called Midjourney. And so by now, DALL-E, which you also, maybe, I don't know when you first heard about DALL-E, it's kind of the first iterations are a couple of years old, and then kind of in the last couple of months, it's really kind of, broke through kind of the mainstream. And that's already fairly old news, which is just indicative of the speed at which machine learning is kind of progressing. And so this is called Midjourney, and it's producing these images. And so that's pretty crazy. This is also an image that is generated by a machine learning algorithm. And, it's not only that you generate images, that are similar to the data set that you have. So for example, in GANs, we saw that we're generating faces, but this was trained on a face data set. And so this is actually conditional models where you control yourself what you want to see. And so it's conditional model is not something that we discussed a lot in the lecture, and we're not going to discuss it here, but basically, okay, not only do you model P of X, but you also model P of X given whatever prompt that I'm giving. And so that's even more complicated. If you look closely, you can see that there are some artifacts here on the image, but kind of, I think that doesn't really detract from kind of the quality of or mind-blowingness of these systems. Okay, so we'll kind of do like baby steps towards, how to build these things. And at the end, I'll share some code that you can maybe during the semester break look at, and you'll be able to code up using all the tools that you learned, like a simple diffusion models without any problem. Okay, so what is the diffusion model? So you read news articles like this, the physics principle that inspired modern AI art. And so as physicists, you should feel proud that, physics is not only are we applying machine learning to physics problems, but it seems like, physics principles are also useful in driving kind of the state of the art of machine learning, further and pushing what's possible. And so that's, okay, you can see, okay, diffusion models generate incredible images by learning the reverse process that, among other things, causes ink to spread through water. So you have like some diffusion process, and you can imagine we're trying to learn the reverse. And so we'll see exactly how this is going to work. And so let's start with diffusion. So, I mean, we can think of just like a few particles. So let's say they are all clustered at a single point. And so what do we mean by diffusion? By diffusion, we mean something like a Brownian motion, like a random motion where, these, dots on the plane are moving randomly in this plane. And so if you're starting to add like random displacements to these particles, it might look something like this, right? And so you basically have a very simple rule. You take the position of the particle and you add some random noise to it. And so in this case, it's two-dimensional noise where to every particle you have random displacements in the x and the y direction, right? So sometimes it's going to the top right or top left or downwards and so on. It's all random, right? But you can imagine if you start with this, because it's all random, they kind of spread out in all directions, right? And so this is something that you can do iteratively, and so you can now add more noise to it and kind of continue this diffusion process, and they will just kind of spread out further, right? So it's nothing crazy. You just basically add noise, and as you're adding noise, these particles just diffuse in all different directions. Okay, so this is, when we say, okay, ink is spreading through water, this is very similar to like, what you might have seen in the thermodynamics lecture, where you have like a container with some gas in it, and so this is constraining the particles to like a specific location, the same way that the particles were constrained on a specific location in this direction, right? And then if you remove the boundary, things will start diffusing, and basically the structure that you've seen before is not recognizable anymore once you do this diffusion many time steps, right? And so at the late stages you will not know, so you'll see kind of what the average position is at the lowest plane, right? And at some point it's all uniform, and you cannot recognize anymore that all the particles at some point were constrained to the left-hand side of this container, right? And so conceptually, what this noise addition does, it removes any structure of the way that these particles were distributed originally, right? So the same way here, there was a lot of structure, and now you're diffusing. And if I would just show you this picture, you wouldn't know kind of where these particles were. They could have also been at the lower left-hand corner, right? And it could be the result of diffusion in that way. Okay, so basically, what does diffusion do? So when we're saying we're adding noise, right? So adding noise is the same thing as sampling from a conditional distribution that is kind of centered at like the previous position, right? So we have our original distribution P of x0, right, where we have all of these points clustered at the plane, and now we sample P of like the next position given the current position. And so that if that is centered around, if the noise is centered around 0, it's the same as saying, okay, we sample around the original position and have like some kind of Gaussian that sits on top of the original position, and then you sample what the new position is. And so we're sampling P of x1 given x0, right? And so we can basically, so this is what's called a Markov chain. So you have like many of these conditional distributions attached one to the other, and so you go P of x1 given x0, then P of x2 given x1 and so on and so on and so on. And so these just kind of represent the different time steps. So let me just try to get this thing out of the way. Okay. And then, so if you wanted to kind of express what the distribution of like the late time final distribution is, you would basically need to integrate over all the intermediate time steps, right? Okay, so this is kind of from right to left, we're diffusing and adding noise. Okay, so you know, if we so now if we add noise, you can imagine, okay, if you're adding noise and you're always adding something, at some point, I mean, it will diffuse into infinity, right? But it turns out if you add noise in the right way, where you're adding noise and then you're maybe also shrinking the entire system, then you can control this diffusion process so that this final distribution, you know, it's not something that you need to kind of solve this complicated integral, but it's something you can, you know, figure out analytically what this is going to be. And so if we're adding noise in the right way, this final distribution becomes our favorite distribution of all time, which is the standard Gaussian distribution in like 1 dimension or n dimensions, right? And so you can kind of see what this looks like. So here on the x-axis, we have time, right? And so all the particles start out at one position. So we have kind of like a delta peak as a distribution on the left-hand side. And now, you know, you're adding, so every particle gets added some noise, and then we scale it in a particular way. And then, you know, you basically get these trajectories. And in the end, if you would, at some late time, you know, histogram, what the positions are of these particles, you would get like of the starting position. And so the way that this works kind of concretely, and it's not super necessary to kind of follow all of the math, you can kind of look up online. I can actually, so I don't think I have it in the slides. I might add it to the slides when I upload them. There's a very nice blog post that kind of goes, you know, in a very high detail through the math. But basically, you have exactly this thing. So how do you kind of add, you know, how do you kind of go to the new position given the old position? So this should be xt minus 1, sorry. I'll just kind of try to fix this. Okay. So how do you sample the new position for the next time step given the previous time step? You basically scale down the previous time step by some kind of constant, and then you add some noise. And so this is basically a normal distribution that is centered on a scaled version of the previous time step, and there is a certain amount of noise that is defined by some kind of noise scale, which controls the variance of the normal distribution, right? And so if you have this, you can basically see, okay, what is the distribution, not only kind of when you go one time step, but you can go n time step, and you can solve it in closed form, what the final distribution or, you know, what, you know, for any number of time step from 0 to t, what the distribution looks like. And it's basically, you know, like a scale version where you multiply 1 minus the noise scale for every time step. So you have beta t is the noise scale, and alpha is 1 minus the noise scale. And so if you multiply all of these alphas together, this gives you this alpha bar, and this you know, gives you kind of what this the center of this final distribution of p of xt is going to be if you start at x0, right? And so now basically, okay, you can see, okay, so the displacement of where the particles are centered around is controlled by this alpha bar, right? And so the question is, okay, what does this alpha bar looks like? And so if we're adding noise with a specific noise schedule, where maybe the noise is increasing linearly, then our alpha t. So if we choose the noise between 0 and 1, you're multiplying a lot of numbers between that are smaller than 1. And so if you multiply a lot of numbers that are smaller than 1, this alpha bar is going to become 0, right? Because you multiply 0.9 times 0.8 and so on. And so this alpha bar becomes 0. And so if this becomes 0, the mean of the xt distribution is going to become 0. And the variance of the xt distribution is going to become 1, right? And so that's kind of with this specific rule on how to do this diffusion process, the late stage distribution, no matter where you start, is going to be a standard normal distribution. And so this is basically just you're adding a lot of noise, but you're not kind of exploding, where all of these particles are, but they're all constrained because you have this scaling step 1 minus beta t, times xt minus 1 in this diffusion process. Okay, so what does this look like kind of concretely? So I mean, this is something you can code up yourself fairly easily, right? And so you can kind of see what this looks like. And so here, so we can kind of look at two different things. So we can look at like a distribution of starting position and diffuse every single particle and see where they end up. And you can see, so this is the top row. And so you can see that, once you're diffusing at the after 700 steps of diffusion, you'll not be able to tell anymore where any of these points was originally in the in the first pane, right? But it's also didn't explode. They're all kind of distributed as a two-dimensional Gaussian, like with standard variance, but you lost completely the relation to the original position. Yes.
In contrast to real diffusion.
Yeah, exactly. Yeah, exactly. In real diffusion, you don't have this contraction thing. So this would be maybe diffusion within like a gravitational field or something like this, where you still get some kind of attraction and things are not just flying into all directions, but they're just kind of mixing up, right? Exactly. So this is easy. So this is like a two-dimensional distribution, which is easy to visualize. In more than two dimensions, it becomes very difficult to visualize the diffusion process for many things at once. But we can look at what this looks like. What is the trajectory of a single particle that is kind of scattering around and diffusing, and what does this look like? And so you start so here's like an example of an MNIST image. And so this, starts out as a MNIST image, but now for every pixel, we're adding some random noise to the pixel. And so for every time step. And so this, produces the sequence that you see here. And you can see, okay, the picture becomes noisier, and you can imagine if you do this for different MNIST images at the very end, okay, it's not possible to tell anymore what the original image is because you just added a lot of noise. It's the same thing, so the noise doesn't explode, so the pixel values don't go into like crazy high values, but they all stay kind of within controlled bounds. And in the end, basically, what this image is at the very right-hand side, it's like one sample from the 784-dimensional Gaussian, right? So where you're sampling what the value is for every pixel independently from a kind of Gaussian distribution. And so like this entire image is as if you would take one point in this two-dimensional distribution and kind of trace it through these different steps. Okay, but so the point is like this diffusion process is something that you can basically run in any like a arbitrary amount of dimensions, and it stays kind of basically all the properties stay the same. Okay, so what's kind of interesting is that once we have this diffusion, so basically we can predict. So as we had like in this formula, we can basically predict what the distribution is, not only like at the late time, right, where we know it's kind of standard Gaussian, but depending on where we are in the distribution, this alpha bar is going to have different values. So at the first moment, it's going to be 1, right? So then and then you like multiply by a small number, 0.9, and so on. And So at any point in this diffusion process, you know by using this formula what the distribution looks like for like this ensemble of diffused particles, right? And so we can actually also look at what the formula looks like here and here and here and here. And so you can see, okay, if you had one, at the very beginning, alpha bar is one, because we start with zero noise in our noise schedule, right? So we had our noise schedule at the beginning. We only add like a very small amount of noise. And so if beta is small, right? So then 1 minus beta is basically 1. And so here you have 1 and 1. And so basically you have like a delta peak. And so that's basically why. So at early times, it's very closely distributed around the original position, as it makes sense, because you didn't have a lot of time to diffuse. And as you're going to later times, it's kind of spreads out and becomes this standard normal distribution. Okay. So one thing that is kind of interesting to observe is that not only can you kind of specify what the distribution is at any point in time, you can even kind of specify how do you go backwards from this distribution. So if you know that you have like a diffusion setting where you start from x0 to this standard normal. Now, if you say, okay, I want to get to x0, how do I go backwards? So how do I go these paths backwards? How do I go from late times to less late times and to earlier times and so on? And actually, it turns out it's very easy. So it's not obvious that you can do this, but actually, it's just like a very simple application of Bayes' theorem, where you're saying, okay, I want to know, okay, how do I go from a late time to an earlier time? So what is the distribution of the earlier times given the late time and given what my original starting position is, right? And so here we just basically apply Bayes' theorem. So this is very simple. Okay, so so you kind of have this posterior t minus 1 given t, and so that you compute it by having like a forward process of t given t minus 1 times the prior. So what is the distribution of t? And then, okay, what is the, so this should be t minus 1, sorry. I'll try to fix this so that we don't get confused. Oops. Right, so this is just Bayes' theorem, right? But what's different from like standard Bayes' theorem, that all of these things are also conditioned on x0, right? So the Bayes' theorem kind of operates between t minus 1 and t, right? But then all of these different things just kind of happen to have like an additional conditioning variable x0, right? Otherwise, it's just standard Bayes' theorem. Okay, so and turns out, okay, if the forward process is Gaussian, and we figured out that all of these intermediate distributions, like all the marginals p of xt given x0, are also Gaussian, then we have we're set up where, like in our Bayes' theorem, it's all Gaussian, right? So our likelihood is Gaussian, our prior is Gaussian, our evidence is Gaussian, right? So these are basically just these kind of where you jump many time steps. And this at the likelihood piece is just our kernel, how we do one time step, but they're all kind of Gaussian distributions. And it happens, that this is very easy to compute in closed form, and the posterior is also going to be a Gaussian distribution, right? And so if you know where you want to go, you also can go back. And so that's kind of interesting. So let's see what this looks like. And okay, so if we know, okay, let's say we sample like randomly some kind of position on this right-hand side. And now we want to say, okay, sample to me, I want to get to x0, right? Okay, how do I do this? But I want to get to x0 by doing a lot of random little steps, right? And so because we know how what these kind of steps look like, right? This key of xt minus 1 given xt and given x0, we know that, okay, we can sample one, time step, another time step, another time step, another time step. Every time we know what this kind of posterior looks like, what this conditional distribution looks like to go to earlier times, giving the late times. And, without fail, we will basically arrive at this original X0 distribution, which is not surprising because, of course, like in this kind of setup where we're saying, okay, how do we sample the earlier times? We're conditioning this on X0, right? And so it's not super surprising that, we managed to go back, right? Okay, so we have this, okay, we sample, da, 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 da. And so we can do this for like a different X0 as well. So we have our Q xt minus 1 given Q xt and X0. So let's use a different X0. And so then our rule changes a little bit because our X0 changed as well. But now we can do kind of the same thing. We can kind of go back and we can basically find a random path towards our original number, right? And so that's kind of interesting. And in some ways, basically this, if we would describe what we're doing is we can basically regenerate X0 kind of stochastically by using this kind of anti-diffusion process. So instead of kind of adding noise, we're removing noise. But it's not something that is like we deterministically jump right away to X0, but it's something where we can do many, many kind of random time steps, but we arrive at the X0 because we have our correct rule, that will lead us towards our X0 from where we started, right? But we can kind of go backwards. And so that's kind of like a start of a generative model, right? So where we start from a random distribution on the right, right? And then we're basically doing the inverse of what we do in the forward process of, adding noise. We're trying to, we basically remove noise. So the distributions will become tighter and tighter. And then, at some point they will kind of converge to X0. Okay, so it's a generative model, but, so how does this Q of xt minus 1 given xt look like? Basically, what you're saying is, okay, so the posterior, so the earlier time step that you need to sample is somehow like a mixture between the current time step and where you want to go, right? Which kind of makes sense. So let's say, you're like at this position, okay, where does the next time step need to be? So it needs to probably on average be somewhere between this X0 where you want to go and where you are right now, right? It's some kind of weighted mean. And so that's kind of what this formula tells you. Again, it's not super necessary for this qualitative discussion to kind of follow all the math kind of, in detail, but you can see kind of qualitatively, okay, the average step, backwards is somehow like some combination of where you're currently and where you want to go, right? Okay, and so then you can also see, okay, what does this variance look like of this posterior? And so conceptually, what we want to have is that this variance should, like as you're going backwards in time, it should become narrower and narrower and narrower, right? And so this is exactly what is happening. So, in particular, this variance is scaled by this beta t. And so you remember early on, we had little noise that we're adding in the diffusion process, and we're adding more and more and more noise. And so, at very late times, this variance will be small because beta t is small, and then you have a very tight distribution, which is exactly what we want to have in this, kind of contracting direction. Okay, so this is how we can go backwards. So this is exactly what I just described. So our kind of sanity checks, I mean, without understanding the formula in detail, we can kind of see that it qualitatively works. Yeah. Sorry? So this should be 1 minus, this should be 1 minus t. Oops. Good point. Thanks a lot. Very good. So let me see, how do I fix this? So something like this. Okay. Great. So, as we said, okay, the mean of this the backward step is, roughly between our current position and where we want to go, and then the variance is sharpening up. Okay, great. So now you might or might not be impressed by this generative model, right? Okay, it's a fairly uninteresting generative model. Okay, it's true that we can found a way to stochastically generate, something in our original data space, but we already gave it the goal, right? And so it's a little bit, underwhelming in the sense that, okay, by following kind of this stochastic process of, starting at some late time and always doing like a previous time step, previous times using conditional distributions, we can produce x0, right? But I mean, our rule already had x0 where we want to go to begin with, right? So it's not like a very impressive kind of generative model, right? We always generate the same thing, but what's important is, okay, so that's not impressive, but what's interesting is that we can have a way to kind of stochastically do this backward diffusion without, kind of where we go step by step from some kind of random position to this x0. So that's interesting. Okay, so let's see. So this is not going to be this is not useful right now, but it's going to become useful very soon. And so, okay, just try to remember. Okay, we know what this looks like. So how we can go back for like a specific target. Okay, so let's see how we can build a real generative model that is going to impress us. Okay, so the idea behind the diffusion model is not that we start kind of in a situation where we had like all the particles clustered at a single position, but where we have a setup where like the original data density is somewhat distributed. And so as we said, for example, for MNIST images, this is going to be a very peaky distribution where you have like one peak where all the ones are in the 784 dimensional space. You have one peak where all the threes are and all the eights and so on. So you have like some kind of high dimensional complicated distribution that you start out with, but you can imagine that all of these like original data instances, you can add diffusion, you can run them forward, and they will all kind of, once you run the diffusion, they will all kind of merge into the standard normal distribution. So all the, if you start diffusing a 0, so you can imagine, okay, let's say these are all the zeros and these are all the threes, right? And if you start diffusing at first, they will still be separated, right? Because you just added a little bit of noise. You can still recognize what this original digit was, right? So here, I mean, here you can still recognize this was a 0, not a 3, right? So in this trajectory, in this high dimensional space, at some early on, these trajectories will still be kind of separated, but as you add more and more noise, they will kind of merge and they will all just kind of look like random noise, right? And so this is the diffusion model that we have. And now what we want to do, and so this is kind of our goal, is we want to train a model that does the backward step, but without giving a specific target, right? And so this is different than what we had before. So here we have a backward step, t minus 1 given t, and given x0. And so there we're always going to one specific goal. And now we want to have something where we go p of x t minus 1 given xt, but no goal given. But the idea is that, okay, if we start out somewhere random here, we should arrive at least in one of the high density regions of this original data distribution. There should not be a path that goes to the low density region. And so this is roughly what we are trying to achieve. And then we have like a real generative model. We start out kind of sampling some easy distribution that we know how to sample from, like a standard normal distribution in 700 dimensions is not a problem. And then we have some kind of rule on how to go into the backward direction. And if we get this rule right, we will kind of arrive at positions in this high dimensional space that where our original data was sitting. Okay. Okay, so this is where we want to go, but what we have so far is only the left-hand side. But you can kind of imagine that the right-hand side is more or less kind of like the average of many little delta peaks. If you would kind of average out the left-hand side over kind of like a distribution of possible x0 values, you get the thing that is on the right, right? Okay, so let's see how we do this. Okay, so mathematically, the thing that we're going to do is going to be structured very similarly to a variational autoencoder, right? And so if you remember, we had a variational autoencoder. We went from a high dimensional kind of data distribution into some latent space where we had like a simple distribution, right? And then we had a decoder that went again to the complicated distribution, right? So we went from data to some space where we had a simple distribution, and then we went back to the data, right? So this was the autoencoder setup, right? And so here it's going to be very, very similar, but now kind of the encoding and decoding step are not just neural networks that do kind of some kind of one-shot mapping, but the forward process is many, many little steps, and the backward process is also many, many little steps. Okay, so where's our forward process? Okay, the forward process is basically, okay, in the autoencoder language, it was called like an inference network where you generate the latent random number given your original data. So this was QZ given X, right? So it's basically, okay, you kind of have the posterior of the data in the latent space. And so here we have the same thing. We have a forward process now that kind of generates this latent trace. So basically like this wiggly line on how you arrive at this Gaussian distribution. And so then, the data, if you sample from this, it's going to be distributed kind of like in the standard normal way. Right? So that's the forward process and what we called the inference network. And now we have a reverse process as well. So the reverse process in the variational autoencoders, we sample from the prior or a P of Z, and then we have a kind of like a simple model where we can generate. So once we pick the latent code, how we can generate data for this specific latent code, right? So we first sampled P of Z, and then we kind of ran our decoder, which kind of gave us the mean of this distribution P of X given Z. Right, and so this is what we had the decoder, and so in this case, it's kind of like the reverse process. So you start out from the simple distribution P of Z, and then now we have a slightly more complicated decoding mechanism, which involves many, many little steps instead of just like one big neural network. But then the idea in the end is the same, that we somehow arrive back at the data. Okay, so in some ways, it's kind of like a funnily structured VAE. So it has like some similarities, but there are also some important difference. For example, one difference is in this VAE, the dimension of the latent space and the dimension of the original space is the same, right? So here, if we're diffusing the image, we're adding noise, but like the amount of pixels is not changing. Whereas in a variational autoencoder, we had like this compression and decompression idea. But I mean, other than that, it looks very similar. Okay, so now the question is, okay, how do we model our forward process and our backward process, right? And so as we discussed, our forward diffusion is kind of like a Markov chain. So it's like this iterative, application of conditional likelihood. So we have P of Z1 given X, and then Z2 given Z1, and then blah, 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 blah. And then you have like ZT minus 2, as a condition, and you sample T minus 1, and then you sample T given T minus 1, and so on. And so this is kind of like a, forward diffusion process as we discussed, right? And so now we can, so it's also an interesting difference to the standard VAEs. And the standard VAE, we train both kind of the encoder and the decoder at the same time. In this example, we fix what our encoder is, so what the forward process is. We define this is the way that we do our diffusion, and the only thing we want to train is how do we go backwards, right? So the forward direction is fixed, and the backwards direction is something that we need to figure out how to do. Okay. So now basically, okay, what we want to achieve is basically this kind of setup. So we start with some kind of data that we sample, right? And then we go forward. In this case, forward is from right to left, right? So we add noise kind of one step at a time. And so you can see originally, like in an early stage, you can still make out what the original data was. At the late times, it's just in random noise. And now, so this is what we know, right? So we know this direction from right to left. What we don't know how to do is we go from left to right. And so we want to have something that goes from late times xt to an earlier time xt minus 1, right? And so this is what we want to achieve. And so the idea is that, okay, by removing noise, you're generating, potential, instances of this data. And so like peaks in this high dimensional data distribution. Okay, so how did we do like a VAE? For VAEs, basically the way that we optimize our VAE is that we optimize or we maximize the elbow. So we had like the evidence lower bound, right? And so we want to maximize the likelihood, or we kind of minimize the negative elbow, right? And so the negative elbow looks something like this. You have kind of the posterior Q of Z given X kind of in the numerator, and then in the denominator you have the joint likelihood P of X and Z, which you can factorize into like a prior and then this generative part, right, where you go from Z to X. Okay, so let's see. So this was, if you remember, how we trained the VAE, and so, but this is very general, so it doesn't tell you what this Q of Z given X should look like, or the P of X given Z. And so now we just do like a different modeling assumption where we're saying, okay, we model this as like these Markov chains, right? And now let's see what this elbow looks like. Okay, so now it gets a little bit complicated, but I mean, in the end, it's going to become very, very simple. You just need to suffer through this for a little bit. And so now, okay, how do we do Q of Z? Q of Z is like this chain of these Markov things, right? And so we just expand this, right? And then at the bottom, we have also our chain of like the P of Z. So here I wrote it in a way that's going to be useful later. So we start at the late time. So we sample from the prior, and now we sample T minus 1 given the prior. We sample T minus 2 given what we sampled here, T minus 1, and so on. Right, so you have all of these different terms, and so they're just arranged in a way that's kind of the times line up, right? And so now you can see, okay, if you stare at this long enough, you'll basically see the following, that all of this, so first of all, you have like a lot of products that look like this. So you have log of like the, T given T minus 1 for the forward process, Q. And then for the reverse process, you have kind of like the same term, but with the times reversed, right? And so here you have T minus 1, here T minus 1, T. Here you have T minus 1 given T minus 2, and here you have the reverse, and so on, right? So you have like a lot of these terms. And so because they're all multiplied together, but they're all in the logarithm, and so the individual logarithms kind of add up. And so you can imagine that the loss is basically dominated by terms that you see on the upper left-hand side. So you have kind of a pair of the forward thing, Q, and the backward thing, P, and then with the times kind of reversed, right? And then the total loss is basically the sum of all of these kind of individual terms, right? So you start to see it's kind of becoming more simple. All right, so let's stare at this guy for a longer time. And so now we can basically say, okay, what do we know about this forward process, Z, so the late time giving the early time, so Q of ZT given ZT minus 1. So we know that it's Markov. So what does it mean to be have like a Markov property? It means you only depend on the previous, like the previous time step, but you don't have any memory where you came from. If you know what your previous time step is, that it completely defines what your next step is, right? And so, another way we can basically, what's going on here? Why is this? Why is there a black box? I don't know. So, okay, so what does it mean to be Markov? We can basically say, okay, like the version with the memory, so where we say, okay, I'm also conditioning on some X, it doesn't really matter. So it only depends on what the ZT minus 1 is. So you can add all kinds of additional conditionings and so on. It doesn't really matter. And so we can, without any problem, basically add this extra X conditioning, right? And so this extra X conditioning, if you remember, is like a well-known thing, and or we can transfer it into a very well-known thing with the following way. So we have our Q of ZT given ZT minus 1, right? So this is conditional likelihood. And so now we can do Bayes' theorem again, the reverse process what we had the other, like a few slides up. So we basically say, okay, we want to do Bayes' theorem on this condition. And so we do now T minus 1 given T times like the probability of T divided by the probability of T minus 1, right? So these three things at the top kind of correspond to this Q thing up here, right? So this is just Bayes' theorem, right? And so now we can basically, because it's still logarithms, we can divide this logarithm up. And so we have one term that kind of looks like this, which we'll discuss in a bit. But what's interesting, the reason there was a black box that should have been colored is that, so this thing, if you remember, is something we know, right? So what is the previous step if we give it like a target, right? So all the way back here. So we have T minus 1 given T given some kind of X where we want to go, right? So how do we go backwards towards a specific target? And so this shows up in this formulation again, right? And so it's really important to realize that this is something we know perfectly well how to handle, right? And now we'll look, so we're kind of happy with this term. We'll kind of look at this term now. And so let's see what this looks like. And so for all of these terms, so remember we need to add up all these different time steps. And so you kind of get terms like this, where you have ZT divided by ZT minus 1, and then the next thing has ZT minus 1 divided by ZT minus 2. The next thing has ZT minus 2 divided by ZT minus 3. So basically all of these terms cancel out, right? And so what you end up with is that really the only thing that matters is this piece. And so this completely dominates the VAE style loss, which is our elbow, right? And so we can say, okay, our elbow is basically just a sum of these different terms, which kind of look like this. So we have our backward step that we know, the backward step with a specific target, compared to the backward step that we want to train, right? And so, but how do we compute the total loss? So this is, averaged over the possible Z's that we have, and it's average over the possible data things that we started in our diffusion process, right? And so this now becomes very, very manageable, and we'll kind of analyze what this looks like. Okay, so we're almost done suffering, but we kind of are starting to kind of see the light at the end of the tunnel. So basically what we're trying to do is, okay, we're comparing our backward step with a specific goal, and to our backward step that we want to train. And now, we basically average over all possible targets that we have, right? So we have not like in our real data distribution, we don't have a delta peak. We have like a distribution of possible targets. And so we want to kind of arrive at each of these targets at some point. And so we're basically saying, okay, we average the distance between the backward, like the different backward step that we have. So every data, like every possible target has like its dedicated backward step. And what we're trying to do is we, train a backward step that is kind of, satisfying all of these things on average. So we have our, so this is basically like a KL divergence here. So we have, sampling from Q, and then we have our Q here and a P here. So this is a KL divergence. So it's comparing the backward step with a specific target X with the backward step that we're training. And now we average over all possible backward steps, right? And so that's pretty nice. And we can kind of get in, so we'll try to get an intuition beyond the formulas in a bit. Okay, so in the end, basically what this looks like, so structurally, if you looked at this, this looks very much like a supervised learning task in the end. So even though we're doing like, variational autoencoders, are kind of like unsupervised learning method and so on, but in the end, what we're trying to say is, okay, we want to minimize or basically what the step is. So the prediction is, okay, what's like the previous time step, right? And so we actually have like what our target should be. And so we're trying to, average or learn this so that it matches this piece, right? And so this looks very similar to supervised learning, because supervised learning was this forward KL mode where we're basically averaging over possible data. So this is the thing that we condition on, right? So in the standard supervised learning, this was P of Z given X. So given the image of the cat or something, predict, what animal it is. And so we're averaging over like specific data. So the things that we're kind of predicting based on, and then we predict what the previous time step is. And we want this prediction that we're training to be close to the prediction, that is generating the data. Okay, so the only thing that is different now is that we're kind of like in this confusing situation where we have multiple labels at the same time. We have multiple targets that we're averaging over. So we have like an additional conditioning here, but in the end, it kind of looks very much like a supervised learning task. Okay, so let's see what this looks like. So unlike the usual supervised learning, we actually know the target. So this is different to what we had in supervised learning. So supervised learning, we only had, we had like those variational forward KL inference where we only had samples and so on. And, we didn't know how to compute this KL divergence in closed form because we don't know what this thing looks like. But in this case, we actually know what this looks like. So this density. And so if our target is Gaussian, so our kind of density to go to a specific point in the data space is a Gaussian posterior. And so our training model is also like our backward step that we're training, we can also assume to be Gaussian. And then in the end, it's like just the KL divergence between two Gaussian densities. And then it ends up to look something like this. The KL divergence between the two densities is basically the difference between the means, scaled by the variance of like the second argument of the KL divergence. Okay, so then you can simplify this even further, and you can kind of ignore the scaling step, and it's basically saying, okay, so the our trained model is close to the conditional to this target model, and we just take the MSE loss like this, right? And so you remember, so if we had like this QZ t minus 1 given t for like a specific x, this was basically like this average between our current position and where we want to go, right? So this was what our posterior looks like. And so basically what we're comparing are these two terms. Okay, so there was a lot of math. It's very difficult to follow, and it's probably useful to try to kind of do this by hand using pen and paper. But I'll try to kind of give you some intuition on what's happening, right? Okay, so what that just happened? So basically, what we said, okay, we want to find like a backward step. We want to go from late times to early times, right? Stochastically. We want to have something, okay, given my current position, I want to randomly sample the next, like the previous position and the previous position and the previous position. So I want to kind of get like a random path from the right to the left. And sometimes I want to end up here, and sometimes I want to end up here, right? So that's kind of roughly what we want to achieve. Okay, so let's see what this looks like. So now then we said, okay, we want to basically train this like a VAE, and so we had like our elbow, we have our forward model and then our backward model. We have our prior, so this looked very similar to a VAE. What's a little bit funny is that you have like these kind of stochastic traces, but okay, the global picture looks the same. And then in the end, basically, we arrived at a very simple loss that looked like a standard MSE loss, where we are taking the where we take the difference between like the like the conditional thing like the backward step for like a specific target with the backward step that we're trying to train, and we weight it by all the different targets that we have in our data set. Okay, so let's see what this looks like. We'll do a very simple data distribution with just two peaks. So like instead of having like 0 to 9 and then many different like stroke styles and orientations of how you have the numbers, we only have two samples. So and we want to have like a backward step that either produces sample 1 or sample 2, right? And so we have two kind of original data items. So what does the forward diffusion process looks like, right? And so this is basically what we had, just kind of overlaid on top of each other. So we can start with samples on the first peak, right? And then we kind of have these green trajectories forward. And then we can start with samples from the second peak and we have the blue trajectories forward, right? And okay, so now how do we go backwards? And so basically what we're saying, okay, we want to start at some kind of position here. And so if we knew that we wanted to go to peak 1, like the problem is solved, right? So this was at the very beginning. We know, if we know we want to go to peak 1, we just have our little rule how to stochastically go to peak 1. And this will give us some kind of posterior on where to go next, given that we're here, right? So given that we're at ZT, which is this red dot, and given that we want to go to peak 1, we have some kind of distribution on where to go next. Okay, fine. Okay, so let's see. Of course, the same thing is happening with peak 2. So we start at the same position. So given that we're still at this red dot, but now we're changing the target, we want to go to peak 2 instead of peak 1. Our next step looks slightly different, right? Which is not surprising because we want to go to like a different place. Right, and so our next step is slightly moved. So if you take kind of this, like if you rotate, basically you want to move more to the right, instead of to the left, right? So here you want to move to the left, kind of a little bit further downwards. And if you want to say, okay, I want to go to peak 2, you need to go further to the right, right? Make sense? Okay. So now we have, but now we have like the situation we want to kind of go to both peaks at the same time. So what are we going to do about this? So what should our next step be, right? Is we don't want to make a decision where to go. And so we only want to have like a model that tells us, given that we're at this red dot, what should our next step be, right? And so basically what is going to happen is that we learn something like this, right? So we just take some average between these two kind of possible backwards distribution, and we approximate it with the Gaussian as well, right? And because the Gaussians, they're not too dissimilar, this approximation is going to be a good approximation, right? If you have like small enough noise steps, the posteriors don't look so different. So you can see, okay, so if you want, so here T-1, you can see, okay, what is the distribution of the green trajectories versus the distribution of the blue trajectories? They're still kind of the same. They're starting to separate a little bit, but I mean, they're still overlapping a lot, right? And so you can see they're overlapping a lot. And so approximating this with like one big Gaussian is going to be a good approximation. So, but now what is happening? So if you're now sampling at T-1 and you end up here, it's more kind of like you sample from this green distribution. Whereas if you sample from this, once you sample from this red distribution, you end up on the right tail. It's more like you decided to go to peak 1 or peak 2, right? And so depending, so you have now this red distribution, now you sample, and by sampling, you kind of make the decision, but randomly, whether or not you go to peak 1 or peak 2. Okay, and so this is kind of what our diffusion model is doing. And okay, so now the question is, okay, how do you actually then kind of continue on? And what's interesting is we have our KL divergence. So, how do you train, what does it mean to kind of match this red distribution to these two peaks, right? So we basically have like our KL divergence. We can compute the KL divergence from our red model compared to each of these targets. right? So we can compute the KL divergence between red and blue and red and green, right? So both give us a kind of some some kind of quantitative value, how close the red is to the green distribution and to the blue distribution. The question is, okay, should we more try to match the green distribution or should we more try to match the blue distribution, right? It's how do we know? And the fact is that the importance of like this specific KL, this specific KL divergence is given basically by the probability of getting like a specific X and Z pair, in the forward process. And so let's see what this looks like kind of instinctively. And so here you can say, okay, let's say you run this a couple of times. Now you're here at this, so this is your current position, right? From this current position, you can still like go to peak 2, right? So there is a posterior, like our standard rule, like this blue distribution, how we kind of go from here to this peak 2, right? Because after all, it's still possible. You could imagine there's a trajectory going from peak 2 to this thing. The problem is just that this is fairly rare, right? So this is just not something that is going to happen very often, whereas like arriving at this position from peak 1 is going to be happening much more often. And so what your loss function does, so arriving at our red ZT given peak 1 is like a low probability. Getting like our green peak here and our ZT, this is high probability, right? And so we want to so because this is high probability for peak 1, we want to weight this KL divergence between red and green much with a higher importance than the KL divergence between red and blue, right? And so it's fine, if you take the probability seriously, your training process will more try to match the green distribution and ignore the blue distribution. And so what does this have as a result? So once you're already here, so what are you going to sample? You're going to sample in this direction. So now you sample like t-1, so you want to go to the next step, but you're basically sampling from the green distribution, right? Maybe rarely you're sampling from kind of this tail here. And so once you're already on this branch, you're still like going to continue, on average, kind of continuing this green branch, right? Does that make sense? Okay. So, and so this is basically what it looks like. So, like a sampling process that will end up at like this peak 1 is going to look like this. At the very beginning, the two posteriors are kind of equally important and equal, like very much overlapping, right? So why are they equally important? Because like once you're here, to arrive at this position from peak 2 or peak 1 is basically the same probability. And so it doesn't really matter, right? So these two KL divergences, so red versus green and red versus blue, are equally important. So it's trying to take an average. Once you're kind of further along the sampling process, the probability decreases to have arrived here from peak 2. And so the learning process will match the, try to minimize the KL divergence to the green distribution much more than to the blue distribution. So this becomes less important. And so you're more moving towards green, which means that next time you sample, you're even more moving to this green direction and even more moving to this green direction. And you're kind of like locking into like a specific like fate, right? And so you start here you still don't know, like this sampling process could have also like put you on like this blue trajectory, right? But it didn't happen because randomly you sample like something here, but because you sampled something here, the next time you sample, you're still like going further into this green direction. Okay, great. So now let's see what the alternative looks like. The alternative basically looks like something like this. So you start at the same position. So you notice the original position at the late time is exactly the same, but it might be that, okay, once you sample here, you like happen to fall on this right-hand side. And now you're kind of on your way towards this second peak, because the next time you sample, you're already kind of in like an area where, the green trajectories are, less represented than the blue ones. And so for our learning process, it's more important to minimize the KL divergence with the blue this density than with the green density. And so this is like a self-reinforcing feedback loop where at the end you're basically only kind of targeting this second peak. Okay, so that's basically what's happening. And so now you can imagine, now we have like two peaks, two delta peaks, and now you can add like a third and a third and a third, and you can imagine how you get like a sampling process for like a continuous density here on the left hand side, right? It's basically okay, for every possible x you have like a specific a bespoke backward step that we know what it would be, and so if you're here, we're basically trying to like minimize the KL divergence for all of these different backward steps, and we weight them by the probability to have arrived at this point by starting from like a specific point here in the data space. Okay, great. So this is diffusion models. And so if you kind of follow this all the way, it kind of looks like something like this. So this is, you can kind of check out the code yourself. So you, this is something you should be able to understand. I mean, maybe not the details because you need to kind of go through the math, but it's kind of, it's like a feed-forward neural network. It's not nothing complicated. And so then you kind of have this thing, and you can kind of see how it's starting to lock into a specific digit, right? So here you're removing noise. Here you still haven't decided because all of these paths are still overlapping a lot. And then as you're moving here, you're kind of already decided that there's little density at the top, right? And so this is not going to happen with like a 7 or something like this. So this is going to be likely already here, already you kind of locked into the trajectory that you're going to generate a 6. How exactly the 6 is going to look like, it's still kind of up in the air, but it's already kind of clear. Here you kind of generate like an 8. It's not like the best diffusion model because this is not Midjourney, but because it's something like a simple feed-forward neural network that kind of runs on my laptop. But you can kind of see qualitatively what's happening. Here you have like you generated 2, and so you early on you already start to lock into this trajectory, and then in the end it's just refining this more and more and more to make the image sharper, right? Okay, so you can kind of check this out on our GitHub, and maybe you can try to kind of generate, use other data sets that are not MNIST, maybe generate some galaxies or something like this. Okay, great. So here, okay, how do you make this jump from these MNIST images to real, real like pictures? Maybe like what you would kind of like what the state of the art was a couple of years ago with these diffusion models. And so it looks something like this. So this is the forward process, right, as we discussed. So you're adding noise, and as you're adding noise, kind of all of these things, I mean, they're not exploding because we're kind of controlling how we add noise. And so they all arrive at this white noise distribution, right? And so we're going from left to the right. And, all of these trajectories basically kind of start overlapping. And so now how do we go backwards? It looks something like this. So now we go backwards. It looks something like this. And you see, okay, as you're kind of as you're going kind of backwards in time, you're locking into like a specific trajectory. And here, like at these late stages